Ian is swimming across a river which is flowing due south. Knowing that the current is strong, he's angling himself in a direction 20 degrees north of due east, while the current is pushing him due south. Assume that Ian can swim 0.7 meters per second in still water, and the speed of the current is 0.3 meters per second. 1. Sketch a diagram of this situation, including the Ian without current velocity vector, the current's velocity vector, and the resultant velocity vector. Use your sketch and the law of cosines to find the length and direction of the resultant. Okay, so we'll begin with the picture. So it says that I am swimming at 20 degrees north of due east. So that means a little bit up from due east. So let's say this is due east right here. In fact, I'll make that a dotted line, due east. And then we're going to estimate a 20-degree angle. And I'm traveling at 0.7 meters per second. So we'll put that as the length of that vector. And then the water is due south at 0.3 meters per second. So from the end of my vector, I'm going to draw something that is due south. And I'm going to draw it so it's a little bit less than half the length of the black vector, because this one is supposed to be a 0.3. So try to get these guys to scale as much as you can. I think it's going to turn out I did not do a good job of getting things to scale, but that's okay. I want you to see what it looks like when you don't do such a great job of drawing an accurate picture. So those are my two vectors, and then we want the resultant vector, which is going to go from my starting point to where the current is going to push me. So that green is the resultant, and that's what we're after. Okay, so what we see here is a triangle. 1, 2, and 3, and we have one of the sides, and we have another side, but we don't have an angle because that 20 degrees goes partially out of the triangle. But what we do know is this angle up here. This angle up here is definitely 70 degrees. And the reason you know that is that if you felt like it, you could extend this due south line and make a right angle there, and then you have a perfectly good right triangle with a 20-degree angle, and therefore the other one must be 70. So definitely a 70 there. If your high school geometry class brings back fond memories, then I could give you another way to get the 70, and that's to draw a north-south line, because that's parallel to the north-south line of the current, and then taking a look at these parallel lines and the transversal that hits them both. And maybe from high school geometry, you remember when you have parallel lines cut by a transversal, then the alternate interior angles, which are what those two guys are called, are congruent to each other. In other words, they have the same measure. And because this is a right angle here, the 20 degrees must have a partner in 70, and that 70 could then get copied over to there. However you get there, you need to get a 70-degree angle, something in your triangle. And so now we'll look at the triangle that we're given, and we have a side, and we have an angle, and we have a side. And what we don't have is an angle side opposite pair, so that means use the law of cosines. So let's see, we know that we're going to end with a cosine of, we'll put this in green because that's what we're finding. We know we're going to end over here with a cosine of 70 degrees. I don't know what to put on the left, but on the right-hand side, it goes 0.7 squared plus 0.3 squared minus 2 times 0.7 times 0.3 times the cosine of 70 degrees. And it's equal to something squared. So how about we call x the length of that resultant vector? That makes this x squared. Okay, and so then the nice thing about this version of the law of cosines is that you can just type the whole thing in one shot. The order of operations will get you where you need to go. So 0.7 squared plus 0.3 squared minus 2 times 0.7 times 0.3 cosine of 70. Now you can do everything right up there, but forget that you need to check your mode, and you'll get a crazy wrong answer. So degrees in this problem. I think that looks okay. So that right there is x squared. And so then we need to do the square root of that thing. X squared is about 0.66. And wait, no. X squared is about 0.43635. And then the square root of that gives me x is about 0.661. x is measured in the same units as the other two sides of the triangle, so meters per second. And then once we know that, we can then find an angle in our triangle. So what we just figured out was the length. Let's see what color we can do here. Purple. So the length of the resultant vector is 0.661. And then in order to get the direction, I guess what we really want to know is what's this angle right in here? Because essentially that's the direction we're headed. You know, are we going like 10 degrees north of east or 5 degrees north of east? That's what we're after. So in order to find that angle, how about we first find this angle in here? Okay, so let's call this guy in here theta so that we can refer to it. And now that I know x, I now think I can use the law of sines. We have an angle side pair. So let's say that sine of theta divided by 0.3 is equal to sine of 70 divided by x, which is 0.661. So that means sine is 0.3 sine of 70 divided by 0.661. And then we can do an inverse sine. So let's get the calculator to help us here. So we're doing 0.3 times the sine of 70 divided by, but don't type in 0.661, do second answer. So we get that, and then we'll do the inverse sine of that number. And we get 25 degrees. Sine of theta is about 0.4268, and so theta is about 25.26 degrees. Okay, no problem. So then we'll come back over here, and that blue angle right there that we called theta is really about 25 degrees. So then we just need to find this angle, and here's where we realize that we have a problem. Or maybe you don't have a problem because your picture was more accurate than mine, but I wanted to show you what to do if you end up drawing something that isn't quite to scale, and you get something like this, which is definitely not valid. I mean, we know that this whole angle is 20 degrees, so there's no way part of it can be 25 degrees. So what do? Well, we say, well, actually, I guess we didn't really draw this diagram to scale very well. So what it really must look like, I mean, theta is definitely 25 degrees. The math here doesn't lie to us. So I'm going to draw my east. I'm going to draw my line up here, and that's 20 degrees. And then we'll draw the blue 0.3 just like we did before. So we haven't done anything different until now, when we realize that, oh, actually the angle that we called theta is 25 degrees means that the blue line actually must cross over just a little bit. We need a 25-degree angle. So the green actually ends up going a little bit below due east. And then therefore our theta angle of 25 is reasonable. So that's the more accurate picture. And it's okay to not know that going into it, as long as you can handle, you know, this information, the 25-degree angle, and then update your picture. So what that means is that the actual angle that is south of due east is about 5 degrees. So about 5.26 degrees south of due east. That's our direction. Okay, so number 2, explain what your answer to number 1 tells you about this situation. So it tells me basically that that the total effect of the two vectors here, me swimming off at an angle and then the current pushing me straight south, is that you know, essentially I'm traveling not entirely under my own free will, but I'm traveling at a speed of 0.661 meters per second at an angle or a direction of 5.26 degrees south of due east. Part of that is my own free will, but part of that is the current pulling me due south. Okay, number 3, resolve the in without current velocity vector and the current's velocity vector into components, assuming the x-axis points east and the y-axis points north. Okay, so the in without current, we'll just draw again. So there was our due east, and then without the current, I was up here at a 0.7 and an angle of 20 degrees. And so in order to find components for me, without the current, we know that x is just the magnitude of the vector times cosine of the angle, and y is the magnitude of the vector times sine of the angle. We've seen this formula in several different guises. Here's the current iteration of the formula. So the length of our vector, the magnitude is 0.7, cosine of, and let's just make sure we're clear that that 20-degree angle is really 20 degrees. That's the standard position version of our angle. So we just put cosine of 20 degrees. And then down here, the y component is the same thing, but with sine. So we'll just type both of these things in. So those are my two components. 0.6578 and 0.2394. And that's it. So then if we really wanted to write my vector, then we would say, oops, we would say that the velocity vector of me without the current is about 0.6578I, that's the due right part, and then plus 0.2394J, that's the up-down part, so up. Okay, and then the current vector, the currents vector, we'll call it C for the current. So the current, we'll draw over here separately. So the current is just straight down at 0.3. So we actually don't need any fancy cosines or sines. We could just say that the vector that is the current is, okay, let's see, there's some I component plus some J component. So how much is this current moving right and left in the I direction? That is to say, how much east and west? And the answer is not at all. So there's a 0 there. And then how much in the up-down direction? Well, it's a 0.3. But that's not quite right because 0.3 would indicate up and we need to go down. So the current, the vector for the current in components is 0I minus 0.3J. Number 4, add the vectors from 3 to obtain the resultant velocity vector. So here we'll do this back in green because that was our resultant color. So we're going to take the 0.6578I plus 0.2394J. And then we're going to add to that the blue vector. Say add here the blue vector, which was 0I minus 0.3J. And altogether we'll get our green answer, which is 0.6578I minus, oh goodness, 0.7606. Is that right? That is not right. 0.0606. Okay, so that's the resultant vector in components. And then on the next page, number 5, explain what your answer to number 4 tells you about this situation. So what that means, again, number 4 was the resultant. So my true path is carrying me at the I component, which was 0.658-ish meters per second, and that was positive, which means east. And the J component was 0.061, but it was negative, which means south, meters per second south. which seems reasonable given the diagram we came up with, the updated version anyway. We were indeed heading east and a little bit south. That 0.061 is pretty close to 0, so we're not heading south with much velocity, but we do have a little bit of downward velocity. Okay, and then number 6, resolve your answer from number 1 into components. Does it match your answer to number 5? Okay, so let's see if we can do this one. So we'll draw one last diagram here. So what did we end up with on that previous problem? I'll just draw the final answer, which was the resultant, which was green. So our green vector was like this. East was here. We decided this was about 5.26 degrees, and that the length of that vector was 0.661. So if we want to get that guy into component form, we'll call this R for resultant. Then we just use the same formula as we had before. We know that the x is the magnitude of the vector times cosine of the angle, and y is the same thing with sine. So the magnitude of this vector was about 0.661. Cosine of the angle is 5.26 degrees, but there's a problem. I'll fix it in a moment. 0.661 sine of 5.26 degrees. The problem is that this 5.26 degrees is not in standard position. So if we want to write that as an angle in standard position, we'd have to say, oh, wait a minute, this was going clockwise from the positive x-axis, so this is really negative 5.26. And after a glutton for punishment, you could say, well, really, it's like 355 degrees going the other way. But why don't we just make it negative? So we'll put a negative sign in a different color there. So again, the idea here, make sure that you are writing when you use these formulas for the components, that you write the angle in some standard version, standard position version of the angle. So we might get a little bit of rounding error because I'm not using second answer, but that's okay. So we get that, and then the other one, 0.661 sine of negative 0.526. Okay, and do those things agree with the answers that we got up there? I sure hope so. So 0.658, that's positive, and then 0.061 rounded, negative. And so that definitely agrees with what we got in number 4. So we'll just put our answers here. So that means that the resultant vector, something I plus something j, the I part is at 0.658, j part is a negative 0.061.